This is an introduction to the mathematics and biology of bird flight. It's hard to cover everything in a short video, but what you will learn is how interesting birds really are. All flight is governed by three equations. The first is the Bernoulli equation, which explains variations in pressure. P is pressure, a derived measure of force exerted divided by the area it's exerted on. Rho is the density of the fluid, and V is the velocity of the bird moving through a fluid. Fluids are liquids and gases, like air, and fluids are continuously deformed under the action of a shear force, like a wing. The second equation solves for lift, which is equal to 1/2 of the air density multiplied by the square of the velocity of the object, the area of the bird's wings, and the coefficient of lift, which is found from the type of airfoil and the angle of attack. An airfoil is the cross-sectional view of a wing and the area above and below, with higher pressure below, causing the bird to have lift. The angle of attack is the angle between the chord, or the line stretching straight across the middle of the wing, and the relative velocity. If a bird is flying parallel to the ground, the relative velocity will be 0. Lift acts perpendicular to the bird's motion. There are actually many different interpretations of how lift works, and there's a big debate between what I just described and many others, including the Newtonian theory, which describes lift as the result of a wing altering the path of the air. Air's properties as a fluid force it to follow Newton's third law of motion and the law of conservation of momentum. The third equation lets us account for drag, which is caused by the difference in velocity between the object and the fluid with which it interacts. It acts in the opposite direction of the bird flying. Drag is equal to the coefficient of drag, which is usually determined experimentally, multiplied by the reference area and 1/2 of the density of the air times the square of the velocity. The reference area, which is also determined experimentally, can actually be multiple things, really any value that's easily measured on a bird's area, like their frontal area or the wing area. So far we've talked about equations for pressure, lift, and drag, in general how flying objects like planes and birds move through the air. Next, let's talk about thrust, how a bird propels itself forward, and see how the math gets complicated. Birds aren't rigid like planes and have shoulders similar to ours in that they can move their wings in an elliptical motion instead of just up and down. Birds generate thrust through the rotations and flapping wings. Modeling this sort of thrust through equations is very difficult for many reasons. We can consider a bird's wing shape and the types of flight birds are optimized for as a way to increase our understanding. When we talk about wing shape, we talk about something called an aspect ratio. This is the square of a bird's wingspan divided by the area of the wings, and it is useful in understanding how birds fly. A bird with a high aspect ratio, such as an albatross, has a large area with which to generate lift, but as it's harder to generate speed, birds with high aspect ratio wings tend to soar. Picture it like the long wings of a passenger plane. A bird with a low aspect ratio or high wing loading tends to experience less drag and can achieve greater speed. However, more flapping is needed to maintain height. Think of the short wings on jet planes. Wings that taper to a point are especially useful in diminishing drag. Wings that are heavily slotted, like those of an eagle or a vulture, generate very high lift and allow them to soar on thermals or wind. To talk a little more about flight styles, we'll go into how different birds fly. Birds that look as though they're lazily gliding through the sky are really just getting the most value from each wing beat and can be categorized as gliding or soaring. A glide ratio refers to the distance traveled forward per unit of altitude lost. The best gliders overcome air resistance by using their body mass to move forward. Soaring is not the same as gliding. Soaring birds take advantage of air rising upwards, such as the obstruction lift caused by wind striking a cliff or building, or thermals caused by the air near Earth's surface heating unevenly. Intuitively, if the bird's sinking speed is less than the velocity of the air rising below it, it can stay in the air indefinitely. Unlike planes, bird flight doesn't just refer to forward motion. Birds, such as hummingbirds or pied kingfishers, can hover, and many birds change their wing shape mid-flight in order to change direction quickly. Wing morphing is the concept that explains when birds change the shape of their wings during flight, like peregrine falcons in a dive. Tucking their wings into their body, the reference area is greatly reduced, allowing the bird to achieve maximum velocity by streamlining itself. Besides beaks and hollow bones, which help to minimize weight, birds have feathers. Because feathers are hollow and are comprised of thousands of barbs, feathers are about equal parts air and matter. Covert feathers on their wings streamline the body and minimize drag, while flight feathers provide stability and control for flying. Birds have muscles which they can use to control their feathers, adjusting for air pressure. Hopefully you're starting to see how the intricacies of biology are actually really beautiful and how the math applied to birds can help us understand our world in ways we maybe didn't even think of before.